Welcome to a short introduction of my latest software, called CQ2. The running program is shown at the right, carrying out a simulation related to particle physics. Probably you heard of CERN, the European Organization for Nuclear Research. Well, the software calculates some aspects of particle physics we explain now. In the left image you see an aerial photography of the biggest particle accelerator of the world, the LHC, located at CERN, Geneva, Switzerland. In its underground tunnel, the Large Hadron Collider accelerates particles by huge electromagnets too near the speed of light. Eventually the accelerated ions, that is nuclei of atoms, collide together in a detector chamber. This creates jets of new particles, which can be analyzed, giving insight into the underlying physics. One investigates which particles are created, deduces their masses and derives additional properties. One important question is whether a particle is fundamental or contains subparticles and which forces are involved. The software calculates an important property of the involved force, being called the strong force. Namely, that this force is unique in that it increases by distance. Particles bound together by this force are nearly free at small distances. If one tries to separate them, however, the force becomes larger and larger, and as a consequence new particles are created. Let us start with the very basics. At school you learned that atoms are made of electrons and nuclei. The nuclei themselves are composed of protons and neutrons. Though the electrons seem to be fundamental, this does not hold for other particles like the proton. The proton itself consists of particles being called quarks. These composed particles are named hadrons, Greek for stout and thick particles. They are themselves classified into the middle-weight particles, called mesons, being made of 2 quarks, and the heavy-weight particles, called baryons, consisting of 3 quarks. Quarks have electric charge as the electron but also come in different flavors, having different masses. The proton, for instance, consists of 2 up quarks and 1 down quark. By combining quark flavors and ordering by some physical properties, one can group hadrons into tuplets. This way the proton, for instance, appears as part of an octet of baryons. Quarks have another property being called color. Quark colors are arranged such that the baryon is color neutral as a whole. An analogy to electromagnetism where the photons realize the according field, the so-called gluons bound together color charged particles. Gluons not only glue together quarks, as their name says, but carry color themselves. Put otherwise, gluons also interact between themselves. The software calculates the quark potential. The strong force is very interesting, as at low distances the quarks move nearly free. This is called asymptotic freedom. In contrast, at separating quarks, the potential increases in a linear fashion. If the energy increases, more and more new baryons are created. This is called quark confinement, and the reason that one cannot observe individual quarks. The calculation is done as follows. Spacetime is discretized as a 4-dimensional hypercube. That is, each cell in time corresponds to an ordinary 3-dimensional cube, and time acts as the 4th dimension. For calculating the potential, it is only necessary to take into account the gluonic fields, simplifying the job. These gluonic fields can be represented by complex-valued matrices. Each side of the lattice is assigned a matrix, that is, each link between 2 lattice points carries a matrix. A stochastical simulation is then carried out. That is, the physical problem of interacting gluon fields is tackled as if it were a problem of a statistical ensemble. In fact, it can be shown that the transcription of the problem is justified from a physical and mathematical point of view. And additionally, that best practices such as Monte Carlo methods can be applied. Monte Carlo simulations, as their name suggests, involve random numbers for generating solutions of systems. Quantum chromodynamics involves 3 base colors. In order to make our simulation faster, we only use 2 base colors, as for this case, the potential exhibits the same behavior. This way, each matrix essentially corresponds to a unit vector of the complex-valued circle. This can be visualized by a unit vector of a 3-dimensional sphere, called the block sphere. We start with a random set of spheres and let the computer shuffle to rotate each unit vector. This new configuration is then accepted or rejected with some probability distribution. This way the configuration slowly iterates towards the solution of our physical problem. As the simulation can be thought of as a thermodynamically game, we carry it out at different temperatures. This is the reason why such a procedure is also called simulated annealing. When the system nears its equilibrium, we carry out measurements. One such observable value is the so-called Wilson loop. This is some closed loop of links. One can think of the Wilson loop as related to the internal energy of the system. The simulation calculates Wilson loops of different sizes. This way finally the result depicted in the shown graph is obtained. By putting the Wilson loops into relation and using some physical argumentation, the behavior of the static quark potential is finally derived. One of the very first Monte Carlo simulations of the strong force potential was carried out by Michael Kreutz in 1980 at Brookhaven National Laboratory. The software actually repeats this pioneering calculation, and the audience is referred to the according paper in the references for details. In the 80s, computational power was expensive. For instance, the Cray 2 supercomputer was available for a pocket money of about $30 million. Its computational power of about 2 gigaflops is now easily beaten by smartphones, such as the iPhone 5s, of our days. The software is cross-platform and open source. Feel free to download the source and compile it for your platform. Running the simulation for a 8x8x8x8 grid on my Android smartphone, a Sony Xperia Z5 Compact, takes about 1 hour. Compiled versions for desktop platforms will be made available on my homepage, and mobile versions will follow on Google and Android stores sooner or later. This videos describe the basics of the simulation for the layman. There is also some documentation for undergraduate students and physicists working on other fields of interest. We have finished now our basic introduction to the software and the involved concepts. If you are interested in further details, how the simulation works, feel free to watch the complimentary video on my YouTube account. Probably you might think that this all is a kind of voodoo, but part 2 actually shows that all this stuff can be derived from first principles by precise argumentation.